Preparing creative dishes with limited ingredients is challenging, and inspiration can be difficult to attain. To address this, we present a deep learning approach to the problem of generative cooking, which involves building a model to map recipe embeddings to realistic images of dishes. So, given a set of recipe ingredients and instructions, our objective is to generate a realistic image of a food item prepared using the given ingredients and instructions. For this project, we used the Recipe 1M dataset. This dataset contains over 1 million recipes, with at least one image associated with each recipe. For each recipe, the ingredients and instructions have been extracted and formulated into embeddings. Our approach was to construct a deep convolutional generative adversarial network architecture that also conditioned on additional metadata, which in this case would be the recipe embeddings. Our training implementation uses loss functions that follow typical CGAN loss, except for the addition of noisy labels to the loss function of the discriminator and a mean squared error term to the loss function of the generator. We used both quantitative and qualitative metrics to analyze the results from our model. For our qualitative results, we examined samples of the generated images and compared them to both the ground truth images and their associated recipes. We found that the outputs showed diversity from the ground truth images, but they still had characteristics consistent with their recipes and ingredients. For example, overall coloring and sometimes texture tended to correlate between the ground truth images and the generated images, while the shape of the food in the generated images often differed from the output images. In terms of quantitative results, we used Fréchet inception distance to measure the similarity of our generated images to the real test images. We normalized this by comparing it to the similarity between our real validation images and the real test images. In both cases, we found that the conditional DCGAN performs better than a vanilla GAN, which is not conditioned on the recipe embeddings. In sum, although the generated images look realistic, there is still room for improvement in tying the ingredients to the outputs. Overall, we believe our model has a lot of potential, not only for generative cooking, but also for other real-world applications involving assembly by parts. Thank you for listening.